reverting to the role of chair. We're delighted to have Evgeny Sobko from the London Institute of Mathematical Sciences, and he's going to talk about learning integrable models from numerics to exact results.
Yeah, thank you. First of all, I would like to thank the organizers for the invitation. And today we'll speak about my first experience of applying machine learning to integrable models. So my main expertise is exactly solvable models like integrable models, conformal field theories. So about 1.5 years ago, I met these great guys, Shailesh and Suvaji, who really knows how to code neural networks. And we decided to solve Young-Buster numerically. Surprisingly, it worked quite good. And today we'll tell you how we now discover new integrable models exactly with analytical formulas. Yeah, by the way, Shailesh is an AI physicist from VIMSA, and Suvaji was a PhD student in City University, and now he works in the AI industry. Okay, so as many of you know, in physics we have the paradigm which is known as the bootstrap approach, which tells us that we should make focus on symmetries, conditions of self-consistency, and try to extract as much information as possible. So probably the first example of such bootstrap program was asymmetric bootstrap, where people in the middle of last century tried to use analyticity, unitarity, crossings, and global symmetry restrictions on asymmetrics to fix it. However, of course, it's impossible to do in general case. However, in dimension 2, we have so-called two-dimensional integrable quantum field theories. So, and in this case, one should add one more constraint to the ordinary asymmetric bootstrap restrictions, namely factorization property for asymmetrics, which tells you that end-to-end scattering can be factorized in the product of two scatterings. And as we know from Alexander and Alexei Zamolodchikov, so this constraint is so restrictive that it allows to fix asymmetrics exactly at finite coupling. So practically what one should do, one should solve the bunch of functional equations like unitarity, crossing, or this cubic Young-Buster, so in a certain functional space, right? And of course, in general case, it's impossible. It's a very complicated problem. And actually, even numerically, there is no general way how to solve such problem because, for example, Young-Buster, you see it is cubic, so problem is non-convex, and there is no general numerical solvers for non-convex problems. So and that's exactly the moment when neural networks comes onto the stage. Because they are very good in dealing with minimization of complicated loss functions. So if you can reformulate your problem as minimization of a certain loss function, then parameterize everything through the neural network and find the quite good low-lying local minimum. So that's actually how we will use them. Actually, today we'll speak about spin chains, and you can wonder why I speak about spin chains if my motivation is two-dimensional quantum field theory. But the point actually is that the key object, so-called R matrix for spin chains, satisfy literally the same Young-Buster equation, and roughly speaking, S matrix for two-dimensional quantum field theory, it is some scalar function times R matrix for the corresponding spin chain. Okay, R matrix is part of S matrix, which captures color indexes. Okay, so and it is a very simple problem. It is finite dimensional quantum mechanics. So Gilbert space, it is just L-fold tensor product of d-dimensional complex space. Hamiltonian is the sum of nearest neighbor interactions. And to claim that this quantum mechanics is integrable, so in other words, it means that there are many mutually commuting integrals of motions. So one have to find such operator R, we call it R matrix. So it's acts from tensor product of two sides in itself, such that it will satisfy this Young-Buster equation, literally the same as in previous slide. So and this boundary condition, which tells you that at zero it should be permutation matrix, what guarantee locality in this Hamiltonian. Then there is some machinery which gives you generation function, for this infinite tower of conserved charges. Particularly, the first one will be Hamiltonian itself, and it can be constructed from R matrix in this simple way. So it's quite dense to slides, but essentially you need to memorize just these three formulas. There was a question, no? Young-Baxter, boundary condition is permutation and relation to the Hamiltonian. Okay, so you have Hamiltonian. If you're able to find such a matrix which solve Young-Baxter, then you can claim that theory is integrable. Of course, you can add many other constraints like unitarity, crossing, some symmetry, hermicity, whatever. So, but main focus for me will be Young-Baxter itself. And another important comment that actually if you already found some solution, you can conjugate it with any matrix from SLD, let's say. So, and it's easy to see that it's again goes through Young-Baxter, it's again solution. So essentially we are interested in the factors or the action of SLD on the space of all R matrices, okay? And there is some bunch of discrete simple things, but they're simple. Okay, so how to solve Young-Baxter? We don't know how to solve Young-Baxter in general case. Roughly speaking, there are three approaches. So first one can be called algebraic approach. So it is about situation when you have some symmetry, let's say Lie algebra, Youngian, or whatever. So, and it brings constraints and it helps you to solve Young-Baxter. So another one is very brute force. You just try to solve functional equations or the corresponding differential equations, but of course you can't go very far because it's very hard. And the third one, which will be very important for us today, it was proposed by Marius Delov and collaborators a few years ago, and is based on the existence of such boost operator, which can, in iterative way, generate high charges just by taking nested commutators. So, and then they just put these constraints, so that charges should commute, it gives some auxiliary system of equations, and they solve it. So practically, again, it's very complicated to go quite far, so they did the two-dimensional case in full generality, found just 14 different classes, but it's quite hard to go further if you don't assume anything. So, but we can do numerics, right? So, so the idea is extremely simple, as I mentioned. So we just have functional equations. So we parameterize all entries of our matrices by neural network. Then we encode Young-Baxter in loss function. Also, we can encode in loss function some other restrictions, like, of course, this boundary condition, reproduction of a given Hamiltonian, hermicity if we want. Then we combine all properties together which we want and build the total loss and minimize it. And it works pretty well. So if we take the most complicated, it's just a proof of concept. Let's take most complicated XYZ model with complicated Jacobi elliptic functions as solutions, and it reproduces everything with very good precision, 10 minus 3, 10 minus 4, which is actually bounded by this number of discretization. If we increase, then we can get better. So, and it works for the families as well. So the main message from the slides that it's trainable problem and the neural network can find quite good solution, numerical solution for our matrix. Okay. Okay, now imagine that we, so here what I did, I gave some Hamiltonian and I asked to find the corresponding R matrix. But I can ask another question. Okay, I don't know any Hamiltonian, I just want to find some integrable model. So then in loss function, I just erase the term which about reproduction of a Hamiltonian. It scans all the space of all spin chains, so, and then it sits at one integrable Hamiltonian. Well, as we will see in the next slide, all these families comes as continuous manifolds. So, and once I found something, it's very easy to explore the vicinity and reconstruct locally this manifold, just making repulsion from one point for a couple of epochs, then turning off repulsion and going back to this manifold. Okay. Good. So numerics works. Now let's discuss these manifolds. How does it look? So once again about this boost operator construction. So this is our initial Hamiltonian, right? Nearest neighbor interaction. This is boost operator. You see it is just formal infinite sum built from this two-point Hamiltonian density, right? And coefficient here A is integer number. Okay. So then higher charges is just commutators. Right? So, and for example, Q3 has this simple form. So then there is conjecture since 90s. There is no proof to best of my knowledge. There is no counterexample. That's actually, it's enough just to fulfill this first commutator, just Q2, Q3. So, and explicitly it has this form, right? So, and you see that it is just a system of cubic homogeneous polynomial equations, right? So essentially, all integrable spin chains form just some algebraic variety which is defined by this set of algebraic equations. So, and families of integrable models actually corresponds to irreducible components of this algebraic variety. So, rephrasing it in normal language of algebraic geometries, what we shall do, we shall take ideal generated by these equations, make primary decomposition, and then because we're interested in factors over SLD, we shall take factors over SLD. Okay, so but that's extremely complicated. Even in case of spin chain with dimension 2, it is 256 equations depending on 16 variables. So you can't use standard things like Grobner basis or whatever. Okay, so yep. But here what is important for us that all coefficients here are integer numbers. So efficiently it means that we work over the field of rational numbers rather than field of complex numbers, right? So in all our Hamiltonians will have relations, polynomial relations with integer coefficients. Yeah, just to mention how simple solution in 2D case. So once again, it is 256 equations, 16 variables, and there are just 14 families, just 14, and 12 of those are just linear varieties, and 2 of those have 1-2 quadratic relations. So it's extremely complicated equations and extremely simple solutions, right? So if from somewhere we will know already some linear relations, let's say in quadratic relations between entries, we will immediately get it. Yeah. So that's actually our strategy. So it's the main slide actually. So how we get exact results? So we start with something reasonable. So for example, we expect maybe some symmetry or something like I don't know, ICE rule. So we need at least in some way restrict our initial variety of all possible things. Practically, we need to fix at least d square minus 1 zeros because in this case we will fix gauge. That's the main thing actually what I want to do in the very initial ansatz. So then I train neural network and try to solve some numerical solution. Well, typically there are very, very small number of solutions. So typically it finds something with greater number of zeros. So there are smaller number of non-zero components here usually. And then we extract by this formula corresponding Hamiltonian, typical precision 10 minus 3. And 10 minus 3 seems so to be the scale where the problem for this auxiliary algebraic equations turns out to be convex already. So in this vicinity, so I can take now old-fashioned method like I don't know, Newton method, whatever, and just try to solve this auxiliary algebraic equations using this data as initial point. Okay, and it allows me to increase precision to 10 minus 10, 10 minus 8 immediately. In principle, it can be even better, but that's already enough. So then I generate the cloud of Hamiltonians with the same precision around this point. So they all belong to the same family, okay? And they have a very high precision. So then I check linear and quadratic relations, polynomial relations, between entries using this known.
Yeah. In principle, this 10 to the minus 8 is because you stopped at 10 to the minus
8. Yeah. Actually, so it is this part is by neural network, and this by me already.
So one more iteration, you get 10 to the minus 16 probably, right?
Well, maybe not iteration, but yeah.
Okay.
Yeah.
Could some of these disappear if you went to?
Well, it never happened so far. So usually, yeah. Usually it works pretty well. That is, well, okay, we'll come to the boundaries of where we are. But okay, so practically it works quite well. And then, so I rediscover many of these simple relations. Usually I just rediscover linear relations. It's already enough. And then I plug them in initial algebraic equations, and it simplifies drastically, and it gives exact Hamiltonian. So and that's just a typical, not very complicated guy. But practically they all kind of the same form. So you see some polynomials, some rational functions here. So, and that's I don't know, how many vertices model. So, and Yep, that's the way how we generate new integrable systems analytically. Okay, cool. Somehow I didn't yet analyze in details these Hamiltonians because people spend years studying kind of 6-8 vertex model. So, but one observation here is that everything what I have found so far has the form of rational algebraic variety. So rational means that there is rational bijection of this manifold into the projective space. Or more practically, it actually means that everything can be parameterized through rational functions. That's correct. And that's, of course, not expectable, right? You have cubic equations, and in this case, 6,500 something, and solution can be written in this parametric rational way. It happens quite rarely in algebraic geometry, and there is some satellite project with some algebraic geometries where we try to prove actually that it will be the case. Okay, cool. What next? So as I said, numbers are growing. So and we think about some ways to optimize things. Particularly this system of auxiliary algebraic equations or even Young-Baxter is overdetermined. We have, let's say, 20, 30 vertices, so 20, 30 variables, and we have hundreds and thousands of equations. So of course we should send, so what we do batching of equations somehow. We choose just some small fraction of equations and train. And it makes loss functions much lighter. So now we want to do it in more smarter way. So we will pick up that equations which makes more significant reduction, improvement in precision. Somehow I give reward to equations depending on their performance and track how good they are. And of course, it's dynamical thinking. If you will use the same equation many, many times, it's getting to be useless because it already gave all information. So that's one of the things. So, okay, about physics, as I said, so modular scalar function, this thing is S matrices of quantum field theory. Okay, so the only thing which we want to implement in this case is analytical properties, because S metrics really care about about position of poles and cuts, because poles are bound states, etc. Right? So you should fix it. So that's only one way how is the best way to implement holomorphic neural network which captures particular poles cut structure. Okay, then of course a matrix of non-difference form. Yeah, so conceptually it's similar. So again there is boost operator. Now it will have one more term. It will be derivative. And now we will get this exact polynomial relations between entries and derivative of entries. But still, again, everything conceptually similar. So, and why non-difference form is interesting? Because as matrices for string sigma model on ADS backgrounds, they are of non-difference form. So, and one of long-standing problem will be, for example, to organize the search of integrable ADS string theories. Yeah. But here we need to implement two things: this analyticity and this non-difference form, more general setup. And in principle, there are many other problems where Young-Baxter appears. It appears far beyond just integrable models, right? So you can build knot invariants from our matrices. You can generate universal quantum gates for quantum computers. Of course, yes, long-range interaction, open integrable systems like Linden-Bloody, and everything reduces to Young-Baxter or some kind of generalized Young-Baxter. That's all. Thank you.
Just wait a moment so that people can
yeah. Sorry, I saw you walking back and forth last time also, sorry. Hi, thank you for the nice talk and very impressive results. I just wanted to ask, so you use machine learning to find a point, and then you do use like this boost method and other things to really hone in on the model that you're looking at. Just wanted to ask you about the machine learning step itself. So how complete is it? Like, can you find all, can you answer such questions using machine learning?
No, it finds something.
Yeah, yeah, it finds something I understand.
So that's the point somehow. You put some restrictions, but usually they are not enough to fix everything. And so especially it is the case in this ADS S matrices. So you fix some gauges and you put some symmetries, but it's not enough to solve equations. So, but then, so we ask neural network to find something, just one representative from this class, several classes satisfying these constraints, right? So, and then we discover corresponding subclass.
Right.
Yeah.
But is there a way to find all possible?
Well, it's different problem somehow.
Yeah, yeah, yeah.
So it is quite complicated because also there is a serious question about checking that two solutions are actually equivalent, for example, as I said, right? So maybe there is some matrix which turns one into another. And if you go to non-difference form like this, as matrices on ADS, there is functional reparameterization degree of freedom. Well, it's getting much more non-trivial even to check equivalence to what you already got, right? So, but for example, here on level of this difference form, in principle, it's quite straightforward. Actually, we actually already do it because because neural network usually wants to attract to some simple models. So, but we already want to find something else. So we can make a repulsion from this submanifold. Actually, yeah.
Very good question.
It wasn't completely clear to me. Have you discovered any new solution that were not constructed before using conventional methods?
Yeah, well, we already discovered, I don't know, numerically hundreds and analytically 15, something like that, because it takes hours for me.
Yeah. But that's the impressive step when I look at it.
Well, this, for example, I know almost everything beyond dimension 2 seems highly likely will be new, because there are very, very few results. I don't know. I should go. This question is about going through all papers in literature and checking did someone already found the same thing or not. Well, I did not see, and I didn't check all of those in such way, but yeah. So if you go, I know, in dimension 4, then it will be anything will be new. I will say.
Thank you. Any more questions? Okay, if not, let's thank Evgeny again.